Linear regression is a popular predictive analysis algorithm. In this video, I will give an introduction to linear regression, then focus on simple linear regression, in which the relationship between one dependent variable and one independent variable is represented by a straight line. Managers often make decisions based on the relationship between two or more variables. For example, manager could consider a high advertising spending may drive sales, so then he may attempt to predict sales for a given level of advertising spending. In another example, people tend to use more air cons during hot days, so a public utility company like Southern California Edison may use the relationship between the daily high temperature and the demand for electricity to predict the electricity usage on the basis of next month's anticipated daily high temperatures. Sometimes a manager relies on intuition and experience to judge how two variables are related. However, if we have data, we can use regression analysis to develop an equation showing how the variables are related. There are several regression terminologies. The variable being predicted is called the dependent variable, or response, and the variable being used to predict the value of the dependent variable are called the independent variables, or predictor variables. For example, in analyzing the effect of advertising spending on sales, a marketing manager would make the sales the dependent variable and the advertising spending the independent variable used to help predict sales. Next, I will talk about how linear regression works, including how to find the regression equation using the least squares method and how to assess the model fit. In the simple linear regression model, the equation looks like this: y equal to beta 0 plus beta 1 times x plus e for error. So in this equation, beta 0 is the population parameter, that is the y-intercept, and beta 1 is the slope of the line relating y and x. The error term e, or in Greek letter we call it epsilon, accounts for the variability in y that cannot be explained by the linear regression between x and y. So the simple linear regression model assumes that the error term is normally distributed random variable with a mean of 0 and constant variance for all the observations. So for example, if we have a trucking company that is trying to figure out how to predict their daily travel time from the number of miles that their driver has driven the truck. So then we call the travel times to be the dependent variable that we're trying to predict, and the number of miles driven will be the independent variable denoted by x. In the trucking company's example, the population consists of all the driving assignments that can be made by the company, and for every driving assignment in the population, there's a value of x mile traveled and the corresponding value of y, which is the travel time in hours. So in practice, the values of the population parameters beta 0 and beta 1 are often not known and must be estimated using sample data. Sample statistics denoted as B0 and B1 are computed as the estimates of population parameters beta 0 and beta 1. Substituting the values of the sample statistics B0 and B1 for beta 0 and beta 1 in this equation and drop the error term because expected value is 0, then we get the estimated regression, which is y equal to B0 plus B1 times x. So to estimate the mean or expected value of travel time for a driving assignment of 75 miles, the trucking company would substitute the value of 75 for x in this equation. So using this equation, y with a caret on top, that is our predicted value. That provides an estimate for the mean value of the y corresponding to a given value of x. In most cases, we refer to y with the caret on top simply as the predicted value of y. B0 is the estimated y-intercept and B1 is the estimated slope. This figure provides a summary of the estimation process for simple linear regression. The estimation of beta 0 and beta 1 are the known parameters of interest representing the population. And B0 and B1 are the sample statistics used to estimate these population parameters. The graph of the estimated simple linear regression equation is called the estimated regression line, with the B0 to be the estimated y-intercept and B1 is the estimated slope. So we have different possible regression lines as shown in this figure. The regression line in panel A shows a positive linear relationship where the estimated mean value of y is related positively to x, and larger values of predicted y associated with larger values of x. In panel B, the estimated mean value of the y is related negatively to x, and so smaller values of predicted y associated with larger values of x. Finally, in panel C, the estimated mean value of y is not related to x. That is, y is the same value for every value of x. Next, I will show how the least square method can be used to compute the values of B0 and B1 in the estimate regression equation. The least square method is a procedure for using sample data to find the estimated regression equation. So we would like to determine the values of B0 and B1 so that we can use this equation to make predictions of y based upon x. So how do we interpret B0 and B1? The slope B1 is estimate change in the mean of dependent variable y that is associated with each 1 unit increase in the independent variable x. And the y-intercept B0 is the estimated value of the dependent variable y when the independent variable x is equal to 0. Later, I will show you an example in Excel and interpret what B0 and B1 means in context. To illustrate the least squares method, this sample dataset contains 10 trucking companies' driving assignments. Each observation or driving assignment in the sample has a value for the miles traveled, or x, and the travel time in hours, or y. We can see that the driving assignment 1 with x1 equal to 100 and y1 equal to 9.3 is a driving assignment of 100 miles and the travel time of 9.3 hours. Driving assignment 2, x1 equal to 50 and y1 equal to 4.8 is a driving assignment of 50 miles and a travel time of 4.8 hours. The shortest travel time is for driving assignment 5, which requires 50 miles with a travel time of 4.2 hours. With this data, we draw a scatter chart. Scatter charts for regression analysis are constructed with the independent variable x on the horizontal axis and the dependent variable y on the vertical axis. A scatter chart shows the data graphically so we can draw preliminary conclusions about the possible relationship between the variables. What preliminary conclusions can be drawn from looking at this figure? Longer travel times appear to coincide with more miles traveled. In addition, the relationship between the travel time and the miles traveled appears to be approximated by a straight line, and it looks like a positive linear relationship is indicated between x and y. We therefore choose the simple linear regression model to represent this relationship. So next, we want to use the sample data to determine the values of B0 and B1 in the estimated simple linear regression equation. For the driving assignment, yi is predicted travel time in hours for the ith driving assignment, and B0 is the y-intercept of the estimated regression line. For the estimated regression line to provide a good fit to the data, the differences between the observed or actual travel times yi and the predicted travel times yi with a caret on top should be small. This is the idea of the least square method. The least square method uses the sample data to provide the values of B0 and B1 that minimize the sum of the squares of the deviation between the observed values of the dependent variable yi and the predicted values of the dependent variable yi with the caret on top. So residual basically is actual value minus the predicted value. Later, I will show an example in Excel and explain this in context. Essentially, we're estimating the regression equation that minimizes the sum of square errors. Although the values of B0 and B1 that minimize equation can be calculated manually with equations, but we have computer software such as Excel, and we can use it to calculate them much faster. I will demonstrate later in Excel how to do this. For the trucking company data in the previous table, we have an estimated slope of 0.0678 and a y-intercept of 1.2739, which minimizes the sum of square errors. Therefore, our estimate simple linear regression equation is predicted y equal to 1.2739 plus 0.0678 times x. So the slope B1 is estimated change in the mean of the dependent variable y that is associated with a 1 unit increase in the independent variable x. So in this trucking company example, we can estimate that if the length of a driving assignment were 1 mile longer, the mean travel time for that driving assignment would be the 0.0678 hour, or approximately 4 minutes longer. The y-intercept B0 is the estimated value of the dependent variable when the independent variable x is equal to 0. So for the trucking company example, we estimate that if the driving distance for driving assignment was 0 units, 0 miles, the mean travel time will be 1.2739 units, or 1.2739 hours, or approximately 76 minutes. So we wonder how we can find a good explanation for this 76 minutes spent but without any driving distance. Maybe the 76 minutes represent by the time you need to prepare, load, and unload the vehicle, which is required for all trips regardless of distance, and which therefore does not depend on the distance traveled. However, we do need to note that so far our simple linear regression model is based on only 10 observations, with the values of miles driven range from 50 to 100 miles, so this dataset is rather limited. It's important to know that the regression model is valid only over the experimental region, which is the range of values of the independent variables in the data used to estimate the model. Prediction of the value of dependent variable outside experimental region is called extrapolation. The estimated value of the y-intercept often results from extrapolation. Extrapolation is risky and should be avoided if possible, because we have no empirical evidence that the relationship between y and x will hold true for x values outside the range of x values in the data that we use to estimate the relationship. For the trucking company, this means any prediction of the travel time for driving distance less than 50 miles or greater than 100 miles is not a reliable estimate because we don't have that data in our origin data set where our model is built upon. So therefore, interpretation of based on the tracking company data is unreliable and likely meaningless. However, if the experimental region for regression analysis includes 0, the y-intercept will have a meaningful interpretation. We can use the estimated regression equation and our known values for the miles traveled for driving assignment X to estimate the mean travel time in hours. For example, the first driving assignment in this table has a value for the miles traveled, and we estimate the mean travel time in hours for this driving assignment to be predicted y1 equal to 1.2739 plus 0.0678 multiplied by 100 miles equals to 8.0539. So the resulting residual of the estimate is the actual miles driven minus the predicted miles driven, which is 9.3 minus 8.0539 equals to 1.2461. So this 1.2461 is the residual for the first observation. Since the travel time for this driving assignment was 9.3 hours, the regression estimate would have resulted in a residual of 1.2461. This means that the simple linear regression model underestimates travel time for this driving assignments by 1.2461 hours, or approximately 74 minutes. So this table shows the predicted mean travel times, the residuals, and the square residuals for all 10 driving assignments in the sample data. Note that in this table, the sum of predicted value predicted yi is equal to the sum of the values of the independent variable y. And the sum of residual ei is 0, and the sum of square residuals ei to the power of 2 has been minimized. So these 3 points will always be true for a simple linear regression that is determined by minimum error. This figure shows the simple linear regression line predicted y equal to 1.2739 plus 0.0678 times x, superimposed on the scatter chart for the tracking company data. This figure also highlights the residual for driving assignment 3 and the driving assignment 5, showing that the regression model underpredicts the travel time for some driving assignments, such as the driving assignment 3. You can see that the residual is positive because the actual value is greater than the predicted value, resulting in a positive residual, and overpredicts travel time for others, such as driving assignment 5, because the predicted value is greater than the actual value, resulting in negative residual. But in general, the scatter chart appears to be fitting the data relatively well. So in this figure, a vertical line is drawn from each point in scatter chart to the linear regression line. Each of these lines represent the difference between the actual driving time and the driving time to be predicted using the linear regression for one of the assignments in the data. The length of each line is equal to the absolute value of the residual for one of the driving assignments. When a residual is squared, the resulting value is equal to the square that's formed using the vertical dashed line representing the residual in the figure as one side of the square. We find the linear regression model that minimizes the sum of the squared errors. So this is the slope equation and the y-intercept equation. Now that we've learned how to develop the estimated regression equation, in this section we want to assess how well the estimated regression equation fits the sample data. We'll begin by developing the intermediate calculations referred to as the sum of squares. Remember that earlier we found our estimated regression equation for the trucking company example by minimizing the sum of squares of the residuals, which is also known as the sum of squares due to error. In abbreviation, it's SSE. So SST is a measure of how well the observation cluster about the mean of the y-line. The value of SSE is a measure of the error that results from using the estimated regression equation to predict the value of the dependent variable in the sample set. We have already shown the calculation required to calculate the sum of squares due to error for the trucking company example. The squared residual or error for each observation in the data is shown in the last column of the table we shown earlier. After computing and squaring the residual for each driving assignment in the sample, we sum them to obtain the driving hours square. Therefore, we measure the error in using the estimated regression equation to predict the travel time for a driving assignment in the sample. Now, suppose we are asked to predict the travel time in hours without knowing the miles traveled for driving assignments. Without knowledge of any related variables, we will use the sample mean as the predictor of travel time for any given driving assignment. So to find the sample mean, we divide the sum of the actual driving times by the number of observations n in the data. So the mean of the y equals to 6.7. The sum of the actual driving time is 67, and divided by 10 driving assignments, that equals to 6.7, which is the mean of the y. Without knowledge of any related variables, we will use the sample mean y as the predictor of the travel time for any given driving assignment. This figure provides insight on how well we would predict the values of yi in the trucking company example using the mean of the y equal to 6.7. So from this figure, which again highlights residual for driving assignment 3 and 5, we can see that it tends to overpredict, that is negative residual travel time for driving assignments that have relative small values for miles traveled, such as driving assignment 5, and tends to underpredict, that is positive residual travel time for driving assignment that has relative large values for miles traveled, such as driving assignment 3. So we use the SST, which stands for sum of square total, to measure how well the observation cluster about the mean of the y-line. So in this table, we show the sum of square deviation obtained by using the sample mean y equal to 6.7 to predict the value of travel time in hours for each driving assignment in the sample. For the ith driving assignment in the sample, the difference yi equal to mean of the y provides a measure of error involving using mean of the y to predict travel time for the ith driving assignment. So the corresponding sum of squares, called the total sum of squares, is denoted by SST. So the sum at the bottom of the last column in this table is the total sum of squares for the trucking company example. So SST equal to 23.9. So in this figure, we show the estimated regression line, predicted y equal to 1.2739 plus 0.0678 times xi, and the line corresponding to the mean of the y equal to 6.7. So note that the points cluster more closely around the estimated regression line than they do about the horizontal line, the mean of the y equal to 6.7. Right, so this is the mean of the y line, and then this one is the regression line. So the data is more closely be around the regression line rather than the mean of the y line. So this shows that the regression model performed better than just using the mean to be a predictor. Now we put it all together. In this figure, we show that estimated regression line and the line corresponding to mean of the y. Know that the points cluster more closely around the estimated regression line than they do about the horizontal line. We can see that the difference between y3 and the mean of the y is much larger than the difference between y3 and the predicted y3 based upon the regression line. So to measure how much the predicted y values on the estimated regression line deviate from y, another sum of squares is computed. This sum of square is called the sum of square due to regression. It's denoted by SSR. So SSR is equal to SST minus SSE. In other words, SSR plus SSE equals to SST. So that is to say the sum of square due to regression plus the sum of square of errors should equal to sum of square of total. So the ratio of SSR versus SST can be used to evaluate the goodness of fit for the estimated regression equation. And this ratio is called the coefficient of determination, as denoted by R square. So R square has a value between 0 and 1, and it can be interpreted as the percentage of total sum squares that can be explained using the estimated regression equation. So the higher the R square, the better the model is. Of course, if you see a R square is over 90%, then there's a potential problem of model overfitting. That means your model is well fitted based upon your sample data, but not necessarily representing the population. So in other words, it's too good to be true, and you've got to re-examine your data set and your method of your predictive analysis process. In simple regression, we have only one variable, therefore only one coefficient. So R square is often referred to as the simple coefficient of determination.